Okay, we're going to talk about geometric sequences. In a geometric sequence, a set of numbers, a sequence is a set of numbers related to by a common rule. All sequences start with an initial term. In a geometric sequence, the ratio of any term to the previous term is constant. This constant ratio is called the common ratio and is denoted by r, where r is not equal to 1. In an explicit form of the sequence, each term is found by evaluating the function f of n equals a times r to the n, or f of n is a times r to the n minus 1, where a is the initial value and r is the common ratio for some whole number. Note that there are two forms of explicit rule because it is permissible to call the initial value the first term or to call a times r the first term. A geometric sequence can also be defined recursively. F of n equals r times f of n minus 1, where f of 0 is equal to a or f of 1 is equal to a, again depending on the way the terms of the sequence are numbered. F of n equals r times f of n minus 1 is called the recursive rule for the sequence. So here is an example of just a little bit of further explanation. R is equal to f of n over f of n minus 1. So your first term is on the bottom, your second term would go on the top, the y values of each of those, and then f of a is the initial term. And then the explicit form would be a times r to the n. So again, pulling those in if you wanted to see what would be actually pulled in. Here's an example of the problem. So we are given a table showing n of 0, f of 0 is 0.2, f of 1 is 1, f of 2 is 5, f of 3 is 25, and f of 4 is 125. So the two important pieces are these first two. F of 1 is equal to 1, f of 0 is equal to 0.2, which gives us our a. To get r, we're going to take f of 1 and f of 0, divide those, 1 divided by 0.2, which gives us r. So the explicit form would be f of n is equal to a times r to the n, which is 0.2 times 5 to the n. So to check it, we're going to check 2, 3, and 4 since we did not use those to find that rule. So put 2 in for n in our rule that we've decided. 0.2 times 5 to the second power. 5 to the second power is 25 times 0.2 gives us 5. 5 to the third power is 125 times 0.2, which gives us 25. And 5 to the fourth power is 625 times 0.2, which gives us 125, which all check according to our table. The recursive rule then is taking our r, 5, times the previous value for the previous y value. So f is 5 times f of n minus 1. So if n is 2, n minus 1 would be 1. So f of 1, we look back at our table, and n is 1, our f of n is 1. So 1 times 5 gives us 5. Then we go to 3. 1 less than 3 is 2, so f of 2 is 5. 5 times 5 gives us 25. So quite literally, we're just taking the previous answer and multiplying each of them times 5. And that gives us our recursive rule. And we can keep doing that forever and ever. But all of those check out. So there are two problems that you're needing to answer. The first one's similar to the one you were just looking at. You have a table given and f of n's, and they want you to find the explicit rule and the recursive rule, and then tell what f of n1 is. And you'll do that on the question in the blanks. And then the first other problem here is the table and the blanks. Okay, to graph a geometric sequence given an explicit or a recursive rule, you can use the rule to generate table of values and then graph those points on a coordinate plane. Since the domain of a geometric sequence consists only of whole numbers, its graph consists of individual points, not a smooth point. So I've already done this problem where you see that 0 is at 81 that was given to us. That is given here. If we take 81 and multiply it by 1/3 or divide by 3, you get 27. 27 divided by 3 is 9. 9 divided by 3 gives us 3. So now we can continue this process and we would complete the table. So 0 is 81, 1 is 27. 3 divided by 3 would give us our fourth number would end up giving us 1. And then on the fifth term, we would end up with 1 divided by 1 times 1/3, which is 1/3, and that is 0.33 repeated. So you can see that we have different points, and we're just going to choose the one that is doing the same as our table. So at 0, we should be at 81. At 3, we should be at 3. At 4, we should be at 1. So that's basically what we're going to look at. 0 is 81. 3 is at 3. 4 is almost at 1. And it looks like it's falling. So obviously, our second option would not be it. And the third one is too much of a straight line. 1 is not at 60, so we're just going to take the first option. Okay. So in this one, you'll just fill in the remainder of the table. So if f of 1 is 5, we'd fill in 5, and you'll fill in what the rest of the problems are on the assignment. Here we show they did not give us the 6, but to find that, we take 1 into 1 minus 1 is 0. 2 to the 0 power is 1, so 1 times 6 gives us 6. And you'll finish that one out. Okay, given a real-world situation that can be modeled by a geometric sequence, you can use an explicit or recursive rule to answer the question about the situation. So we have another problem example. A particular type of bacteria divides into new bacteria every 30 minutes, which means it doubles every 30 minutes. You begin with 200, so we're trying to figure out how many bacteria would be there after 4 hours. So our R becomes 2, our A becomes 200, and to find N, we take 4 hours times 60 minutes divided by the number of increments. Since N is in 30-minute increments, we're dividing by 30.
I was doing a challenge, so I couldn't really stop.
Sorry about the daughter in the background. Please be quiet, Gabby. And it gives us 8 increments. Can't wait for increments. So our f of n is 200 times 2 to the n power. Our recursive is 2 times the previous f of n minus 1, where f of 0 is 200. And so we can use a table or we can use the explicit. This is the explicit rule being used, where it's 200 times 2 to the 8th power, which gives us 51,200. Or we can draw a table counting out the number of increments, not the number of minutes, the number of increments, and doubling each answer after for the f of n's until we get to the 8th increment, 51,200. So one final problem for you to do. My computer catches up. And this is very similar to the one we were just looking at. Again, you're going to do the explicit rule, use shift 8 to get the exponent, and the recursive rule, and then tell how many bacteria will be after 3 hours. This is not the same exact problem I was doing, but it is set up very similarly.